In this section, we're going to talk about the basics of probability. So first we have some definitions. So we're going to have some random procedure. So this could be something like flipping a coin or rolling a dice or drawing a card out of a deck of cards. So an event is any collection of results or outcomes of a procedure. So for example, if we were rolling a six-sided die, and an event could be rolling a 3, okay? Or we could say it's rolling a 3 or rolling a 5. So it's just something that could happen from your procedure. A simple event is an outcome that can't be broken down into simpler components. So for example, before I said, if we were rolling a dice, rolling a 5, for example, would be a simple event. You can't break that down. However, if we say something like rolling a 3 or a 5, those are not simple events because we could break it down into either rolling a 3, so that would be one simple event, or rolling a 5 would be another simple event. Okay, our sample space for a procedure so it's the list of all simple events. So we're listing anything that could happen from a procedure, and that's called the sample space. Okay, and then we have some notation. The notation, we call this P of A, where we have our A in a parenthesis, and this is the probability that A occurs. So what's the probability that A happens? Okay, now probabilities have a very specific range. Probabilities can range from 0 to 1. 0 means impossible, and 1 means definite. It's definitely going to happen. And then anything in between, for example, 0.5 would be a 50-50 chance. Now, you can also write this, we can write it different ways. So this would be the same as saying from 0 to 100%. Okay, so I guess I already said this, but the probability of an impossible event occurring would be 0. So, that's just something that can't happen. So, for example, if we say you're rolling a six-sided die, what's the probability of getting a 7? That probability is 0 because there's no 7 on the die. So the probability that an event that's definitely going to happen is 1, or 100%. Okay, we have 3 different ways that we can write a probability, either as a fraction, as a decimal, or as a percentage. Okay, and when we do have a decimal, we're going to round that to 3 significant digits. Now, to count significant digits, if there are zeros before the number, they do not count as significant. If there are zeros after the number, they do count as significant. So here, if we have this decimal, the first one, and we want to round it to 3 significant digits, we would have 0.438. Okay, the 0 in front is not significant, but the rest of the digits are. Okay, for the next one, we have 0.043, blah, blah, blah. That first 0, we don't consider it a significant digit. We still have to put it in there, but then we put 3 digits after that. So we'd have, the one above should have been 0.439 if we rounded it. And this one would be 0.0439. Okay, and so similarly, if we put another 0, our 3 significant digits, we're going to have 0.00439. So those zeros in front are more like placeholders. They're not considered significant digits. Okay, now we have another definition, what's called a complement of an event. And a complement consists of all outcomes. So a complement, if we call it, say, of event A, consists of all outcomes where A did not occur. And we'll talk more about complements in future sections. So, for example, if we say event A, rolling a dice, is rolling a 3, then the complement of that would be rolling a 1, 2, 4, 5, or 6, anything but a 3. Now, to find the complement of a probability, now the complement of A, the notation we use is A with a bar over it. If we want to find the probability of that, it would be P of A bar. And to find that, we can take 1 minus P of A, because the probability of everything happening would be 1, and we'd subtract off the probability of A happening, and we get the probability of the complement. Okay, so now we're actually going to look at some examples. So let's say we're flipping 2 coins, okay, or flipping the same coin twice. So what could happen? Well, that's called our sample space. And what we do to write our sample space is we make a list with these curly brackets. So the first coin we could get a head, and the second coin we could also get a head. Or the first coin we could get a head, and the second coin we could get a tail. Or the first coin we could get a tail, and the second coin we could get a head. Or the first coin, they could both be tails. Okay, so that's our sample space, the 4 things that could happen. So if the event we're talking about is getting 2 heads in a row, well, the probability there, we take how many times that happened, 1, out of the total number of things in our sample space, 4. So there's a 1/4 chance of that happening. Now, A bar would be everything but head, head. So it'd be head, tail, tail, head, or tail, tail. And there we see there's a 3/4 chance. And that's the same as 1 minus 1/4. Now, we could talk about having 2 children. In our sample space, if we're talking about boys or girls, well, we could have a girl, then a boy. Or we could have a girl and another girl. Or we could have a boy, then a girl, or a boy and a boy. So if our event is having 1 boy and 1 girl, well, it doesn't matter what order they're in. There's 2 different ways that can happen. So 2 out of 4, which is the same as 1/2. Now the complement of that would be they're having 2 girls or 2 boys. And we know that's 1 minus 1/2, which is the same as 1/2. Okay, then now we're going to look at rolling a die, a 6-sided die. So our sample space, we could get a 1, 2, 3, 4, 5, or 6. So if our event is rolling a 5, the probability of that, there's 1 way that we can get a 5 out of 6 things in our sample space. And so the complement of that would be 1 minus 1/6, or 5/6. Okay, now if we're rolling 2 dice, okay, our sample space is going to be bigger here. We could get a 1 and a 1, or a 1 and a 2, 1 and a 3, 1 and a 4, 1 and a 5, 1 and a 6. Or we could get a 2 and a 1, a 2 and a 2, 2 and a 3, 2 and a 4, a 2 and a 5, or 2 and a 6. Okay, now we're going to do this all the way until 6, so I'm going to pause this and write them all down. Okay, so here we see them all written out. You know, whatever the first one can be, whatever the second one can be. So if we count how many we have there are actually 36 possibilities or events. Okay, so the probability of rolling a 3 and then a 5, well, that only happened one way out of 36. Now the complement of that would be rolling anything else. And we would take 1 minus 1 over 36. And here we would get a probability of 35 over 36. Now, sometimes we can make things what are called tree diagrams, and these help us find sample spaces. So to make a tree diagram, we first list out what could happen the first time. So if we're flipping 2 coins, the first coin, we could get a head or a tail. Now, off of each of these, we have to put all of the possibilities for the second coin. So if we got a head the first time, the possibilities for the second one are still head or tail. And if we got a tail the first time, the second time we could get a head or a tail. So now our sample space, we kind of follow down the tree. So first thing we can get a head or a head. Or second, we could get a head and then a tail. And with the tails, we could have a tail and then a head, or a tail and a tail. Okay, so flipping 3 coins, the first coin could be a head or a tail. The second coin off of each of those, we could have a head or a tail. And then the third coin off of each of those, we could get a head or a tail. Okay, so now to write our sample space, we could have 3 heads, head, head, tail, or head, tail, head, head, tail, tail, or tail, head, head, tail, head, tail, 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 head, or tail, tail, tail. Okay, and then very similarly for having 3 children, it's actually the same exact tree, except instead of saying heads and tails, we're saying boys and girls. So I'll draw this now. If you work this out, you'll see that the tree is exactly the same, except we've replaced heads with boys and tails with girls. And then the sample space looks exactly the same, except for boys and girls. Okay, now there are 3 types of probabilities, 3 different things we can talk about. The first one is called the relative frequency approximation. And in other books or something, you might hear this be called experimental probability. So to find the experimental probability, you're doing some experiment over and over. And to figure out what the probability of event A occurring is, you would take the number of times A happened in your experiment divided by the total number of trials in your experiment. And that's how you get the relative frequency approximation. The second approach is called the classical approach to probability. And here, every simple event must have the same chance of occurring. And if that's the case, to find the probability of event A, we would take the number of ways A can occur and we would divide it by the number of different simple events. And then the third type is called, which we won't really use very much, but it's called subjective probabilities. And here, to find the probability of A, so P of A is estimated, we just kind of guess at it. So using knowledge of relevant circumstances. So just by knowing things around it, we estimate it. Okay. Now, when we talk about the relative frequency approximation, or the experimental probability, we have something called the law of large numbers. And the law of large numbers says that as a procedure is repeated again and again, the relative frequency probability so gets closer to the actual probability. So what this is really saying is if you're doing some experiment to find a probability, the more times you do the experiment, the closer your answer is going to be to the actual probability. Okay, so we'll see an example of this on the next page. So let's say you have a coin, a penny or whatever, and you can do this for yourself. You'll get different numbers. And let's say you flip it 10 times. Then maybe out of 10 times, you get 6 heads and 4 tails. Okay, then your probability of getting heads using the relative frequency approach would be 6 out of 10. Okay, or 0.6, 60%. And your probability of getting tails would be 4 out of 10, or 40%. Now, we know the actual probability of getting a head, assuming it's a fair coin, is 50-50, so this isn't exact. Now, if you flip a coin 100 times, you might get something like 54 and 46. Okay? Then you would have 54 out of 100, or about 54%, and 46 out of 100, or 46%. And these are obviously much closer to 50-50. Okay, so here, these numbers support the law of large numbers. And if you do it for yourself, you should see that the more times you do it, the closer you'll get to 50-50.